Hi everyone, welcome to the week 2 of graphs. In the previous week, we covered the different terminology that is associated with graphs, the various ways to implement different types of graphs, as well as the ways how we can traverse the entire graph data structure. In this week, we'll be covering different algorithms or we'll be solving different problems that can be solved using graphs, which are one of the non-linear ordered data structures. So today specifically we'll be talking about this problem of shortest path, and we'll be seeing one algorithm in depth on how to solve this problem. So when we discuss different problems that are associated with graphs in first week, we covered this problem of ST path, which is there a path between vertices S and T in a graph? So given you have like two different vertices, in this case, like let's say if you have this graph, it doesn't have to be necessarily a connected graph or not. uh, we try to find whether there is a path between vertices x and y, or in the first case, let's say a and c. So yes, there is a path here because we can traverse from a to c, or we can traverse from a to b to d to c. And let's say if we ask this question, is there a path between a and q? There's no path because it's not connected for some reason. Or if we say if there's a path from F to A, there's no path because F has no outgoing edges. So there'll be no path from F to A in this directed graph. Now, the solution to this problem, like how we can solve this, is like let's say if we have two vertices that are given to us, and if we are asked whether we there is a path or not. There's actually an equivalent stepping question as well, which we were trying to discuss last week, but we couldn't. So like it's already on stepping. So how we can do that is you can just traverse this entire graph starting from a source vertex or this S vertex, and during the traversal, if you encounter T at any time, that means there's a path from S to T. So let's say if we are talking about a BFS, how we are going to start with the traversal for a BFS is we'll start with the source vertex A, and next we are going to print all the children which are one level up that are connected, which is B and C will be printed. Next, we are going to print the children which are two levels up, which is D is one of them, and then C has one child E, which is another one of them. And then in the final iteration, we are going to print like F. So we know like if there's a path between A and F, if F is encountered in the BFS, if like let's say if we are trying to find between A and Q, since Q was not in the BFS, like when we are trying to push the vertices in the Q, that means the Q is not connected, or there is no path between A and Q. Similarly, if we have DFS, we can just do a DFS traversal, and if we find um this Q, this Q, or this vertex T in our DFS traversal, that means there's a path from A to Q or A to T. So this will actually return whether there's a path or not between like two vertices or that are provided to you in the question. So this is the code for DFS that we discussed last time in our last lecture. So you need to just make one change in this, which is like this is the iterative way to solve the DFS. We are using a stack and we are inserting elements into the stack. Finally, we are like running our loop and pushing different children into the stack till the stack is empty. So here we make just one change, which is when we are pushing either of its children, which is like in the first iteration, A will be on top of the stack. In the next iteration, we'll pop out A, we'll print that A, and next we are going to push its children B and C. So when we are doing this operation, which is when we are pushing these values into the stack, we can check whether B or C is the destination vertex, or this T vertex that we are looking for, which is what I'm doing right here, then we return true. Otherwise, uh, it like there's a there's definitiveness that there's no path between A or S and T, two different vertices S and T, if our stack is empty and we have still not reached that node or that destination. Similarly, you can do the DFS like this. This was for DFS. Even if you apply the BFS, it would exactly look the same. Just replace the stack with queue and the operations of stack with queue operations. The lines of code would exactly look identical, which was we are going to compare V with destination vertex. Now, another way to do this is using a recursive approach, which is you perform the DFS recursively instead of doing it iteratively by using a stack. So this is the code for the recursive one. Basically, what you do is you call this helper method that takes in both your graph source destination as well as your visited array or a visited set that keeps track of which vertices have already been visited. And within this helper method, you repeatedly call this helper method by calling the nodes, like by changing the neighbors, or you first call like A. So you basically call DFS A. Next, within this method, you are going to print A, and then you are going to call DFS of its neighbors, which is DFS on B and DFS on C. And similarly, you are going to print these values. So when are you going to stop this is when you one of the sources that you have passed into this method is the node or the vertex that you're trying to look for. So in this case, like let's say if I'm looking for A, uh, and within the method, like if that source is equal to the destination I'm looking for, you'll just return true, which means there is a path. So it's exactly same. Like just think over this code. It's a recursive way to doing to do the same problem. We are also going to cover this in one of the problem solving lectures. Now, the problem that arises with the ST path is the algorithms do not consider the weights. So let's say if we have this graph, and if I ask you to perform, like to find out whether S and T are connected or whether, let's say, A and C are connected. In this case, like let's say if you implemented the DFS algorithm, how it will work is you'll start with this A node. Now you will go to one of its child. Like let's say if we use the tiebreaker that the lower child is chosen first. So in this case, you are going to go to B. Next, you are going to go to D. And then finally, you are going to go to C. So if you perform a DFS, this will incur the cost. Like if there's a weighted graph, like let's say if it is maps or something like an application which has weights associated with it, typically the cost associated with traversing the path is not the number of nodes, but the total sum of the weights, which is like this problem of shortest path like, is again divided into two components. The first one is shortest path, and the other one is shortest weighted graph or shortest weighted path. So for the first problem, which is shortest path, that's pretty trivial because it's always going to be like if you use a BFS, that will always return the shortest path between two nodes, which is if you do a BFS, it will always give you the shortest path. But if the graph is weighted, then you will not be able to get the shortest path from BFS, like which we are going to see in the next example. But for the DFS, like I'm making this claim that if you perform this DFS, it's going to give you the sum of which will be the path will look something like this, which is A, B, D, and C. Now A to B is 10, B to D is 15, and D to C is 20. So if we add all these numbers, this is equal to 45. But you can see like A is already connected to C, so the shortest path might actually be uh, just this directly going from A to C, which is like 25. So this is not working for the weighted graph. Now, if we apply a BFS on the same graph, it will work because now A to C is now equal to 25. So, uh, like if we apply a BFS, it would look something like this, which is we are comparing C with the destination node or B with the destination node. So in the first iteration, it will return true, and the path will be like A to C, which is 25. Now, let's say if we have another graph, like this is the same graph here, but with a different value of the edge, which is 250 here instead of 25. Now here, if we perform BFS, we again get a wrong answer because when we compare the destination node, which is we are trying to find a path between A and C. So when we compare the destination node with C, we found it in the first iteration of the BFS, which is A to C is 250. Now this is wrong because we know like if we had performed a DFS on this one, it would then give us like it will go from A to B, then it will go from B to D, and then D to C. So which will give us a total path length of 30 plus 15, which is 45. So although we expect it to take a shorter path, now it's taking a longer path because of the BFS. So the BFS works accurately. Again, I'm like telling you, if we want to find the shortest path between two nodes, because it will always give you the right answer. But if we were to find the shortest weighted path, there's no guarantee that it will work because in this case, you saw a counter example that it's not working. So, like I've just summarized these examples here, you can read them. So, if we take the path from ABDC in this DFS, it will be greater. And if we take the path AC in this BFS, like to traverse from node A to C, uh, these are two different examples for two different graphs. So, how we can fix this? Like this problem is again called the shortest weighted ST path is through different algorithms that we are going to discuss in today's lecture. So, for the purpose of the course, we just focus on one of them, which is called the Dijkstra's algorithm. The other ways to solve this problem is using Bellman-Ford, there's Floyd-Warshall, and there's A-star search that is also used. But the top three ones, which is Dijkstra's, Bellman, and Floyd-Warshall, are the most common ones. A-star is in completely different paradigm. Like let's say if you take the AI for games course, you're going to go over A-star search, but it is pretty similar to the Dijkstra's algorithm. These are just like tweaks in the Dijkstra's algorithm. So if we talk about the time complexity of these different algorithms, Dijkstra is fastest in terms of like when you compare with everything else, followed with Bellman-Ford and followed with Floyd-Warshall. So I'm keeping A-star search out. And why this is fastest is because it has like less constraints. Um, it has more constraints, I'm sorry, because we are trying to find a single source like the Dijkstra's algorithm is to find the path between a single source to all other vertices. So if we have A that we provide into this algorithm, like it can have any source, which it could be D, F, E, C, B, or A. You provide that into this algorithm, and it's going to return the shortest path to each other vertex. So it will return a shortest path from A to B, from A to C, from A to D, from A to F, and A to E. Now this algorithm works just for directed graphs. So you have to make sure like the graph is directed. In fact, actually it will work for undirected as well. But what you have to do is if you have an undirected graph, you just need to change it into a directed graph. Like let's say if we have this graph that is an undirected graph, you can change this graph into an undirected graph by changing it with two edges. So it will work perfectly fine by replacing each undirected edge with like two different edges. Now, no negative weights are allowed, which means if we have this graph, like if this has like -5, Dijkstra's algorithm will not work, and no negative cycles are allowed. So this no negative cycles are allowed. It's mathematically impossible because, like, let's say if we have these two nodes in a simple graph with -1 and -2, this is mathematically not possible because, like, if we go from node x to y, like we can take this path -1, then we can go to this one. It will be like -3, the sum, and then it will be -3 -1, which is -4. So it will technically tend to infinity. So there's no way to solve it. But let's say if there are negative weights, there are some problems that require you to have like negative weights on some of them, which is, although the sum of this entire cycle is like 25 minus 14 and 6, which is 12 and 5 19, it's not, it doesn't have a negative cycle. So that's a key distinction. So Dijkstra's algorithm doesn't solve any of these, which is like if you have these, it doesn't work. Like it is not intended to give you a correct answer. It might give you, but it will not always give you. So to avoid that constraint, we have this Bellman-Ford algorithm, which is again like single source to all the vertices, but in this case negative weights is allowed. It is kind of like one level up over the Dijkstra's algorithm because you are technically performing the Dijkstra's algorithm, but you repeat the Dijkstra's for each vertex one at a time. So typically, like if the number of vertices is one v, so you repeat this Dijkstra's algorithm v minus one times, and there is some proof associated with it why it works. But Dijkstra's is the most common one and the most useful one, so we just covered this one in the course. But if you are curious to know, like you can just check out your notes for Bellman-Ford. It is pretty straightforward. It isn't that complicated once you understand the Dijkstra's algorithm. Now, Floyd-Warshall is another algorithm that is one level up over the Bellman-Ford because it has like even less constraints, because now we are trying to find out the shortest path between every vertex, which is what will be the shortest path between A to B, what about A to D, and then from B to A, B to D, B to C, and so on. So it finds the shortest path for all the different pairs of vertices. So even if you like think about it intuitively, Dijkstra's will take the shortest amount of time, followed with Bellman-Ford because you are technically repeating the Dijkstra's algorithm v minus one times. So whatever is the complexity for Dijkstra, like if you multiply that with v minus one, that's the complexity of Bellman-Ford. And Floyd-Warshall is again like I think it's on the order of v cube or v to the power 4. So it takes even more cost, like when running this all pair shortest path. A star search is completely different. We are not going to discuss it, but it's a modification of Dijkstra's algorithm where we have heuristics. You're going to like see this in one of your later courses because it's also commonly used. But for the sake of the course, again, we'll be just using Dijkstra's. I'm going to cover an example in the next video, and then we are going to see like how to implement it. Like I'll just discuss the pseudocode. You won't be asked like the pseudocode in the exams, but it's good to know like how it is working because we'll be solving some few practice questions. That's all for this video. Thanks.